At this time, you should have already had a chance to go ahead and try different size cuts and have the appropriate volume then calculated. And what I basically have over here is actually a spreadsheet that would actually represent some of the different values possibly you came up with. Maybe one of your first cuts was at, a 1-inch cut, meaning that I removed basically 1 inch from each corner. And what that's then telling me is if I remove 1 inch, I can then see that what I have here is I have a length of 6.5, a width of 9, and a height of 1. And then possibly you tried many different variations of that, trying to see, hey, what size cut's actually going to produce the most volume for me? And maybe you were looking at it and things went through your head like, am I getting a larger volume if I have a taller prism or a wider prism? And so hopefully those were types of things that, were just like stirring in your brain a little bit. As we take a look through, we can actually see that, here I'm starting at around 9, and then I'm increasing, getting the whole way up to around 66. And then after I get above 66, I start decreasing again, 65. But then once I get down, I see 37, I'm going to continue decreasing. So something unique's happening right around this area here. And we could see that our size of our cuts around like 1.5 or 1.7. But this would be if we're just kind of using trial and error. Maybe there's a better means to do this. Because in theory, the cut doesn't have to end at the 10th of an inch, if you would. We could go to the 100th, or possibly even the thousandths, or as close to precision as we need. So then the question becomes, how could we actually come up with the actual maximum volume based off of a piece of paper being 8.5 by 11, or a piece of steel for our case? So let's take a look at this then. If we think about the situation at hand, we remember that volume of a prism is length times width times height. And we see that we're going to be removing 2 x's from both sides on both our length and our width, and that our height will be equal to x. So that would give us the ability to write an equation, 11 minus 2x, 8.5 minus 2x, and x. And again, the reason for the 2x is because we're subtracting them on both sides. Here I'm subtracting them from both sides. So now, what I can actually do is I could say, all right, here's an expression that represents my volume scenario. So let's now go ahead and we'll type that into our graphing calculator, and let's see what the graph looks like. So I'm going to go ahead, I have it all typed in there, I hit graph. And at first, something unique looks to happen, right? This looks almost to be linear, but I have to remember, this is going to produce a cubic. So it's going to be a cubic, and my leading coefficient is going to be positive. So, all right, I should be going down on the right. I should be going up on the right and down on the left. But I think it should look more like a squiggly type of feature. So maybe my window's off. So let's see if there's more to it. And here we go. We could see that we weren't actually seeing the entire graph. Now we can actually see the entire graph. And from here, there's a couple things that we notice. One of which is the fact that it looks like right here we have a maximum. And then it dips down, it actually becomes negative, and then we actually get numbers over here that are even higher and higher, if you would, especially, from this point and above. But the question now becomes, why aren't these values over here possible? Because our volume equation only works for certain x values. Can you determine what x values are actually acceptable for our volume equation? And if you're thinking about it, or if you're still thinking, you can pause the video at this time. But the largest our x value can actually be is 4.25. So now the question is, why is that? Well, let's think about it. We had the smallest dimension at 8.5. So if I take a cut of 4.25 and another cut of 4.25, I would no longer have that dimension. Hence, we can see that this 0 right here is occurring at 4.25. So therefore, in analyzing this situation, the only part of the curve we're going to actually observe is this first kind of like parabolic shape. Now you can see it's not purely parabolic. It's actually kind of skewed over here to our left side. But now what we want to do is keep in mind that we're trying to maximize our volume. So if I'm trying to maximize the volume, I need to figure out what the max or the local maximum rate here is. So I'm going to go ahead and calculate. I'm going to hit maximum. And for the left, I'm just going to use a value of 0. And for the right, I'm going to use that value of 4.25. And now what I see here is that whenever I have a cut, so whenever my cut is oops, that really got crazy there on us. 1.5854, and there's still more going on. We get a volume of 66.1482, so on and so forth. But now we actually have a precise value of our cut. So maybe you were close, and maybe your guess was 1.5, or maybe your guess was 1.6 as far as how many inches to cut. But the precise answer would be actually found by using the maximum command on our calculator, getting a cut size of 1.585417708. But in the grand scheme of things, what we want to be able to do now moving forward is be able to take a look at a graph and be able to find what are referred to as local maximums. Now, local maximums are called local maximums because this value right here is not actually a maximum of the polynomial itself. As we stated before, we could see that this value over here is higher, and it actually keeps climbing to positive infinity. But this local maximum is the value that we had actually used to help us solve the scenario provided for us in the lab. Just in closing, then I want to also identify that not only do we have local maximums, we could also have local minimums. As you can see, again, this is called a local minimum because there's still points over on this side that go further down. But this now leads us with a final closing question. How would it be possible for a polynomial to have a local maximum that's an actual maximum? I wonder would it have to be true. We'll get that answer next time we see you, either in class, on Zoom, or on the next recording.